दो उसमें से दो ही रहने दे बस, ज्यादा नहीं खाऊंगा, मीठे हैं ना।
Good evening to all the participants and dignitaries present in this online meeting. Good evening and welcome to all the participants and dignitaries present in this online meeting. I, on behalf of the organizing committee of the ATAL online FDP, I extend a warm-hearted welcome to our resource person, Dr. Saurav Kumar Sahu, to deliver his sessions. Dr. Saurav Kumar Sahu is a senior engineer with expertise in inverter controller validation, hardware in the loop systems, and advanced energy management solutions. Backed by several years of experience in research and automotive industry, he currently drives HIL development and validation for e-drive and high-performance IC engine systems at Magna Steyr, India, focusing on 800 volts inverter ECU testing using D-Space Scalexio and Vector HIL. His technical proficiency includes high voltage and low voltage lab car development, full vehicle validation, and dynamic validation for electric vehicles. He has extensive experience in D-Space HIL for both component level and system level testing, ensuring robust validation and compliance with ASPICE and global standards. Dr. Sahu's expertise encompasses traditional powertrain systems, high-performance internal combustion engines, and electric vehicle architectures with a strong focus on real-time simulation using Typhoon HIL and MATLAB Simulink. He leverages automated test environments for comprehensive functional and interface testing, ensuring robust validation across component levels and system level domains. He also holds TUV high voltage certification for EVs, demonstrating expertise in safety critical validation. Dr. Sahu earned a PhD in electrical and electronics engineering and is certified in ISTQB and ASPICE PAM 3.1. His contributions include multiple high-impact publications and patents in EV charging infrastructure and inverter control systems, reflecting his commitment to advancing sustainable mobility and high-performance validation frameworks. I most humbly request Dr. Sahu sir to kindly start his session.
Thank you, Deep sir. And I would like to thank the organizing committee for giving me this opportunity. Uh, just give me just a minute. So is my screen visible?
Yes, sir.
Hello, madam.
And
Good evening, madam.
my mic
నేను
is
ఎస్ఆర్
clear?
యూనివర్సిటీ నుంచి
Voice is
మాట్లాడుతున్నాను
clear?
మేడం, అసోసియేట్ డీన్.
Yes, voice is clear, sir. Saurav sir, please unmute your mic, sir.
Is it audible now? Hello?
Yes, yes.
Okay. So today's topic is like electric vehicle testing, ensuring performance, safety, and reliability. So in this throughout this session, it will be like a conversation with you all. So whenever you feel like asking a question, you can ask. I want to make it two-way communication so that we can both, like me and all the audience, can take most of the things from this presentation. So feel free to ask questions. I will try to answer all of them. And if not, then later stage I will giving you the answer by the mail. So first of all, why testing is necessary? We are seeing the vehicles on the road, and I would like to tell you over here is like I would go slowly so that what I think is this topic may be new to most of the participants. So if I'll go slow, then you will have questions, then you can ask me. Okay, so let's start. So why testing is necessary? Like we have a vehicle, so why we do testing and what kind of testing we do? Why some specific kind of testing is necessary? Why some specific kind of testing is mandate by government? Why reliability testing is being done? Why reliability is required in testing? And what is safety critical testings? Why we need that? So all of those things, I will try to answer this question throughout this presentation. So prior testing some equipment or some vehicle or a component of a vehicle, we need to have a in-depth knowledge about that component. Example, what this component does, what is its functionality, like what is it end user functionality, what is its engineering functionality. For example, I am sending a signal, what kind of response I am expecting. All those details a tester should know. So, and how to test those signals or the customer functionality, that also the tester should know. To know all of this things or the criticality, to understand its criticality of the test, we need to understand the kind of testing that we are doing. So for that, we need to understand some standard which is given by International Certification Board like ISTQB. Then we need to have some safety critical test. For example, in our vehicle, we do have brakes, we do have ADAS system. So for them, we need to analyze how much safety critical that component is and what are the what could be the adverse effect if those systems fails. So that is being explained in a spice, we call it automotive spice. Then we as we are using a electric vehicle, so the primary battery of the vehicle could range from like hundreds of volt to 800 or 850 or even 1000 volts. So to deal with such voltage, we need to have a in-depth understanding how the system is working and how the what are the safety hazards that could happen during some servicing or some development stage or during the testing stage. So those are being told by TUV. And prior testing for most of the German OEM, we need to have a in-depth understanding for these three components: how it is tested, what is safety critical, and what is high voltage and how high voltage could impact us. So these are the basic founding blocks. So in my daily work, I do develop various hill for component testing and system testing. Those hills are vector hills and D-space hill. Basically, we are using this two type of hills. Then testing could be of a transfer case ECU. or a inverter ECU, or we can have a full lab car or subsystem bench. When I say subsystem bench, in a vehicle, we do have different subsystems. For example, ADAS could be a subsystem, telemetry could be a subsystem, powertrain could be a subsystem. So we do test them in a segregated way, and we call it as subsystem bench testing. Then for prototype vehicle testing also is being done. So whenever there is a vehicle, so prior the main release of the main vehicle, we do have different prototypes. So we need to test them as well. And in the automation end, I use ECU test. ECU test is a tool for automation, and for subsystem bench, we are using some Raspberry Pi and Vector Hills. Now, why EV testing matters a lot, or I can say why the testing of a vehicle, a customer-centric vehicle is needed. So, from the data, the data I have taken, current data I have taken, here you can see the rapid growth in global EV sales. So when we are selling billions of vehicle over the world, so we need to understand what kind of adversaries could happen and how to tackle those adversary, and we would try to minimize that. So testing is nothing but minimization of the risk. So as we are transitioning from what I can say IC to electric mobility, there are several challenges with electric mobility. So that need to be addressed. Like we have a high voltage battery pack, which is in the vicinity. Like let us say we have a 6 to 700 volt or 800 volt DC battery pack. So which is in a compact environment. So and the user is using that sitting on a metal thing. So we need to take care of all those things, and we need to consider the safety critical things as well. So testing for this kind of vehicle where high voltage is involved is very much essential. Then you must be seeing the EV fires. Okay, then EV range limitation. For example, let us say the nameplate the nameplate range of a vehicle is 500 kilometers, but we see that the actual vehicle range is 300 kilometers. So that range limitation is also there. So we need to find out why the nameplate rating is not matching with the real time, what I can say, performance. All those things need to be considered and tested prior releasing that vehicle to the mass market. So this is the main reason of testing. Now let us come to EV market growth forecast segment wise. Here also you can see the in the year 2034 we will have a 1000 billion USD size of market, EV market. So when there is a this kind of EVs are on the road, and we know that there are certain safety critical things that could happen in the EV. So we need to test it in a reliable manner so that it will not cause any issue on the road. Now we'll come to the overview. So these are some of the, sorry, do we have a question? Hello, am I audible?
Yes, you are audible.
Yes, yes.
Okay. So these are the some basic components that we have, but this is not limited. So battery pack, we do have wide range of battery pack starting from 48 volts to up to 850 volts. Okay, so those battery packs could be of different configuration. So if we'll compare two battery packs of similar voltage, if we'll compare them, so there is a high probability that the internal structure of those two battery are not the same. So if that is the cause, then we need to verify both of the battery packs, even if the rating is same. So there could be some different type of battery packs, like in normal vehicles, you see battery pack is beneath the floorboard. There are some vehicles where the battery pack could be segmented. In the figure itself, you can see the battery pack is segmented like left, right, and back. So there could be a chance that some portion of the battery pack could be beneath the back seat and could be sometimes could be front of the bonnet. So when the configuration of this battery changes, the testing requirements and the criticality assessment or the safety assessment will also drastically change. So we need to take care of all those things. Then come electric motor and inverters. So these are the two critical parts that is responsible in the powertrains. Okay, so we need to, when I say we are testing a battery pack, there are two kind of testing involved. One is the software testing, another is the hardware testing. I am considering that the hardware that is present in my vehicle is of no, there is a no fault in the hardware. Okay, so when we take that kind of battery pack, over that we have a controller and we do check the software inside the controller as well. Similarly, for electric motor and inverter, we do have software for electric motor and inverters. Here, you need to note one point that all these components are interdependent. For example, battery pack has direct correlation with inverter and electric motor. So when there is a issue in the software of the inverter, there may be a issue. That issue could be due to the battery pack software glitch or hardware glitch or a communication glitch or a communication glitch between the motor sensors and the controller of the inverter. So when there is a testing is done for a particular component, we do consider all dependencies, all possible dependency with that component. Then different power electronics equipment, as I said, battery management system. In battery management system, if you ever have open a uh, EV battery, you will see there are BMUs inside the battery. Okay, we do have a BMS. Beneath that, we do have BMUs, and in the terminal itself, we do have some relays and sensor arrangement, which is directly connected to the BMU controller. So we need to test from the relay end to the BMU. We need to test all of the things. When we say BMS, it includes all of the things. Now, vehicle control unit. When we test a vehicle, we say in academia, when we say a VCU, that means a brain of a vehicle, and which is responsible for all and everything that happens in the vehicle. But that may not be true in real sense. Why I am saying that, if we'll take a modern electric vehicle, there will be at least 45 to 60 ECUs, and every ECU has its own functionality own capability and own responsibility. Although it sends, depending on its applicability, it sends a signal to the VCU for sure, but most of the things are being taken care of the ECU itself. If required, then that ECU will send a signal to the VCU. So when we are testing a VCU for a vehicle, we need to consider all of the components that is being connected or uh, in any manner is affecting the performance of the vehicle control unit. Then charging system. When we say charging system, again, when we test the charging system, the uh, charging system, the testing of charging system includes motor itself. We cannot, what I can say, only we cannot test the charging system in an isolation manner. We need to consider the BMS, the battery, the motor, the inverter, everything. So charging system. So likewise, I said here also we need to consider all of the things. Now let us go for the level up testing. Usually the there are three broadly there are three type of testing: component testing, system testing, and full vehicle testing. So you can imagine it as a, what I can say, a pyramid where we have a component, then system, then vehicle testing. Okay, so let us take an example of a vehicle, electric vehicle, and when we take an example of electric vehicle, it has various components. So anyone from the audience would like to tell me what are the basic components present in an electric vehicle? Or you can, if you can segregate like powertrain, then body. Can anyone tell me? Am I audible?
Yes, sir.
So can you tell me like what are the things, what are the broadly classifications in an electric vehicle?
Uh, there's a motor is there.
Yeah, which comes
Trans
under powertrain.
right. Okay.
Yes. Then,
And battery system.
yeah, the primary battery comes under the powertrain.
Okay.
Okay. So we do have a huge number of uh, components, but basically we can segregate it as body, powertrain, chassis, right? These are the basic, what I can say, uh, classification that we can do. So in powertrain, we could have BMS, we could have EVCC, we could have uh, VCU, we could have EVAS, we could have intelligent power distribution unit, we can have MCU, we can have GS, we can have ACM. These are the some components of the powertrain. So let us take an example where for the inverter. So uh, I am a company and I do make inverter for electric vehicle. So let us say Dr. Acharya, uh, Dr. Acharya wants to build an electric vehicle company, and he comes to me and tell me like, I want a electric vehicle whose range must be 600 kilometer at least. It should be a coupe. This kind of information, if someone gives me and tells me to design a component, here in this case, it is a inverter. So I would make a sheet, I would write a document where all these requirements are being written, and according to that, according to the requirement of the customer, I will make a inverter. So that should take this much of current and all those things I will consider, and I will make a inverter, which is nothing but a component of a electric vehicle. So prior giving that inverter to a company, for example, if Tata is a company and Tata wants to make a EV, Tata will not build the wheels. Tata will not build the what I can say the inverters. Tata will not build the seat. Maybe Magna Sitting will build the seat. Maybe BYD will make the inverters. Some other company will make the wheels. Some other company will make the VCUs and all those things. And Tata will assemble all of them. Okay. So prior giving those components to Tata, the company itself will perform a component level testing. That means I have an inverter and I do know my inverter's input and output depends on some issue. Maybe I will take those issue or I will simulate signals of those issue, and I will give input to those signal, give input of those signals to the inverter, and I will test how my ECU behaves. So this testing is called component testing. So then let us say I have another four devices. So I will, the Tata will take those four devices and it will assemble and it will do the system testing. Then when all the systems are working fine, then the vehicle testing will be performed. Now here, if you think of an inverter, inverter has different components. Let us think in the perspective of a component developer or component supplier. So for our inverter, there are some signals which comes from some different ECUs. So those could be signal input to my inverter ECU. My inverter ECU gives some output signal to other ECUs. Those could be signal output. Let us say there is a dependency on the there is a dependency of the inverter on the machine, some signals of the machine and the drive. So the now you can see in the left hand side figure there are several components in the inverter itself. Okay, so if my product is an inverter, I could think like component testing could be something different. So I could say mm, the components of the inverter. For me, the system testing for the inverter maker, the system testing will be testing of the inverters only. Okay, so it is the perspective. If you look in the from the perspective of a vehicle manufacturer, the inverter testing will be a component testing, but for a supplier who is supplying the inverter, it could be a system testing for them as well. So when all the components are being tested and uh, then all the components are being integrated, then vehicle testing is being done. So we cannot directly test this what I can say component. We cannot integrate this component and directly assemble that in a vehicle and test. Why? Because there are some safety related issues and in the first iteration that may not work. So for that reason, we do have different type of test benches, and finally we do have lab cars to validate the customer functionality that is being provided by the original equipment manufacturer, that is OEM. So now to give you a better understanding, let us consider this image. This image is being taken from a spice document where you can see there are two sections. Above section where sys is being written, and in the below section where software engineering process group is being written, SWE. From it starts from SWE1 and ends with SWE6. So let us take the same example of the electric vehicle with the uh, demand of what I can say stakeholders, that I want to have a electric vehicle whose range should be minimum 600 kilometers. It should be a coupe. It should pass global NCAP with 5.5 star rating on, like these are the high level requirement that someone will give, which comes under SYS1. In the upper part of the screen, you can see System Engineering Process Group. All the things comes under SYS1. We called it requirement elicitation. Then after receiving that, a technical person will analyze those requirement. Okay, if the range is 600 kilometers, what could be like, he will dig down into that 600 kilometers, what size of battery pack is required, and all those things he will find out. If it is a coupe, what is its size, and all those things in all aspect he will analyze the requirement, which comes under SYS2. Then to hold all these requirements, there should be some framework, some architecture which will hold this requirements. So there is an architect who design the architecture of the vehicle, like to have this range, someone needs to have this component. Okay, so the architect will decide that what to take, what not to take, how the system should look like, and it will come under system 3. Then as I am as someone is explaining the requirements, and someone is writing that requirement and defining all the system requirements, architectural design. So if I will define, and how I will know that this was the requirement and my vehicle is now ready, if the requirement is correct or not. So you will see in the left hand side against all SYS and SWE, in the right hand side you have a test. Okay, so in SYS you will see SYS 5, system qualification test. So the requirement analysis is being done, but as are those requirement are fulfilled? To know that, we need to perform SYS 5 testing, that is system qualification testing. So let us say someone fixed some architecture, so we need to test if that architecture correct or not. That is system integration, the system integration that we did, if it is correct or not. The integration is perfect or not. The integration is as intended or not. We need to find out all those things. So for that, every SIS or SWE has a test predefined. Okay, so let us come to the software engineering process group. Then the architecture has now decided, like my vehicle will have some components, some architecture. Now the engineer will analyze for this hardware to work, what software I need. So every hardware in the vehicle has a software component to it. So we need to analyze for working of the hardware, what software, what kind of software, what kind of architecture. So let us take an example of um, a, um, website. booking website. For example, in that the booking website is being designed for 1000 hits per minute, but some good movie came and the hits cross that 1000. So the the booking website will not function as intended. Okay, so why it is not functioning as intended? Because the architectural design was for 1000 clicks only. Now we are having 2000 or 3000 clicks. So similarly, in the vehicle, the for the hardware to work, we need to have a software which should be capable to run the hardware with the rated, what I can say, the rated capacity. So that analysis is being done by system architecture design. And once all those things are finished, now the SWE in SWE3, the software detail designing and unit construction start. For example, in the same vehicle, let us take a side mirror. When I am long pressing the button, the side mirror is continuously going down. Okay, so my engineer should deep dive to that requirement, and he or she will design a control logic which will detect two touches, like a short touch and continuous touch. With short touch, it will down to some degrees, the glass will get down to some degrees, and if I am pressing it like for some seconds, the total glass will go down. So this kind of detailed design should be done in SWE3. So now this detailed designing is being done. So once the detailed design is being done, then we need to test. So this unit that I have constructed for the side mirror is working or not. So this basically being done by this testing basically being done by a developer only. So developer has the requirement, like I have two type of touch. One is short touch, one is long press. When short touch is for this many millisecond and long touch is for this many millisecond. Okay, so he will give the input and he will verify the intended output. Okay, so once he gets the intended output, and not only the side mirror, everyone will do their job. For example, side mirror, inverters, ADAS system, then BMS, everyone will do their unit construction. Then one integrator, there will be a integration engineer who will integrate all those softwares. Okay, and he will give us the software. From here, SWE5 onwards, the tester's work start. So here, what the tester will do, the tester will perform the integration test, software integration test. For example, if the side, what I can say, I'm taking a virtual example, which is not true for easy understanding. For example, if my side mirror is open. Okay, so in that case, my roof should not open. So in this case, there are two components, the roof and the side mirror. Okay, what I need to do, I need to check if the integration of the roof and the side mirror are correct or not. Here, my intention is not to check my primary intention is not to check the functionality. My primary intention to check the integration is done correctly or not, because uh, functionality is being tested at the SWE4 level already. It is not like that I will not check, I will check, but my intention is to check the integration part. in SWE5. Okay, so once all the things are being done, then we'll go to SWE6 where software qualification test. So prior starting this work, we have started with like my software should be capable of doing this thing. All those things are being written in a requirement document. I will test against all those requirements if the test are passing or not. Now, once the test is passed, then I will integrate the system, like the hardware, software, all those things I will integrate, and I will go for system integration testing in SYS 4. On finishing the SYS 4, then I can go for SYS 5, that is system qualification testing against the requirements that is being decided in SYS 2 in the initial stage. And then, like I said, this company belongs to, let us say, Dr. Acharya. Then Dr. Acharya will have a user acceptance test against SYS 1. So he will drive it, his guys will drive it. So there will be some proto vehicle, and he will analyze, I am a user, I have this criteria. Is those criteria is fitting to my, what I can say, is the vehicle output is fitting to my criteria is not. That is user acceptance testing. Okay. So this is called as V cycle. If you'll Google it, V cycle, it is very famous for testing. So normally in our day-to-day research life in PhD, we do all of this thing in SWE4, SWE5 level. Like first we test our piece of code which is being, let us say, we have a 33 bus system. In 33 bus system, we have several controllers. First, we make the controller and we check with a single node only. So that is SWE4. And as we are a developer and tester as well in PhD, so that is SWE4 only. Okay. Then we do test the integration. Sometimes we take help from our colleagues, like colleagues or some IEEE standards that we could put in SWE5 if it is a software, like in some real-time simulation environment. Okay. So this, in this way you can relate. Now let us come to, do anyone have any question in this slide? Am I audible?
Yes, sir.
Yes, sir. Yes, sir. Audible. Audible.
Okay, okay. So do anyone have any question? Okay, fine. Then let us start from the component level testing. How originally in the in person, how the testing is being done in industry. So here I will take the same example of an inverter. So let us go through this some of the tests, like battery testing, motor inverter testing, NVH testing, BMS testing, and the tools I will explain. Then in battery testing, we do have capacity testing, we do have charge discharge cycle testing, thermal testing, and thermal abuse testing, cycle efficiency, life cycle, we call it life cycle efficiency testing. All this testing could different could differ from what I can say, OEM to OEM. Some basic tests are definitely constant, but the testing could be very different from one OEM to different OEM. And same for motor inverter testing, efficiency mapping, torque and speed curves. Uh, uh, these are the, what I can say, these are the very uh, upper level. I am saying like these are very non technical words I can say, because when I'm saying inverter testing, in inverter there is SI, signal input, signal output, ED, EM, then different time types of tables, all those things we test. Okay, so in our research articles we do not consider all those things, but in reality we do test everything that is possible in the inverter, which could create a devastating effect. That could be a very silly thing, but we do test it. Then NVH, in BMS testing, we do test SOH, SOC estimation, if those estimations are correct or not, fault detection. For all of this testing, uh, we do have different testing devices or setups. So someone could totally work on inverters, someone could totally work on battery testing. So it is very rare that in industry someone is testing batteries, motors, NVH, everything. So someone will test only one or two component. Okay. So in the right hand side image, you can see uh, there is a issue under test which is colored green. So the issue normally, if you have seen it, it normally looks like a Texas Instrument card. Okay, but differ in size. It this issue do have different connectors, different sensor. When it is testing, when we do testing in the control environment, some of the sensors are being manipulated. Okay, we do have some signal conditioning. Then this is the basic block diagram I can say. First, the ECU under test is being connected with a signal conditioning unit. Then the signal conditioning unit is connected to a lab box, and this interface unit is also connected to a programmable power supply. This Scalexio, then this lab box is connected to a RTPC, and the with the help of a jiggling cable, that orange color cable that you can see in the left side of the image, then this RTPC is being connected with a host PC where we perform all the tests. This is a normal flow of a component level testing. So this is a descriptive way how the ECU is communicating with the host computer and how testing carried out. So as I said, let us take an example, so the same example of the inverter ECU. The inverter ECU is connected a interface board. In that interface board, you can have n type of connectors. Actually, it depends on the requirement that we get. So the designer will design the interface board in such a way that he or she will cover all the requirements that is given to him. I'm taking a generalized one. So there could be some DB50 connectors. There could be some I2C connectors. There could be some JTAG connectors, CAN lean connectors, and high speed data cables as well for HPCs. And this interface board is connected with a lab box with a DB50 connector. And again, this lab box is connected to the RTPC with high speed communication, and with LAN communication, RTPC is connected to the host computer. In the host computer, the tester will execute everything. The interface that we get is from the host computer, and the host computer fires the jobs to the RTPC, and RTPC execute all the tests in the environment. So now again take the take a example where example of this inverter where we need to check some functionality. Consider a virtual functionality. If I will send a signal 1 to a invert to the inverter issue at some pin, I will get square of it. Okay, so let us say I send a, I will get a square. So how the data will flow? So first of all, my automation int, I will come to the control disk first. So we do have a specific software flashed into the inverter ECU first with the help of a ECU software flashing interface. That could be any flashing software. Okay, there are different kinds of flashing software like vFlash and all. Okay, so using that software, we will flash it. Or sometimes when some flashing mechanism doesn't work, we use JTAG port and directly flash binaries into the memory of the ECU. Okay, so consider the software is being flashed successfully into the inverter now. So when the software is flashed successfully, we'll get some pop-up like the software is being flashed automatically. And in configuration disk, we have configured all the DB50 pins, like to which pin I will give which signal. I have done that in configuration disk in configuration disk with the help of MATLAB, and I have compiled the model and load that model into my control disk. So in the control disk, when I will send A to, for example, let us take an example of pin number 1. When I will send A to pin number 1, I should get A square from pin number 10. So I will check that response in this host PC. So as I have mentioned, there are some standards that that is defined in ISTQB that I need to obey. So I will not only send A, I will send B, C, D, E. So what to send will again is again topic. So that decision what to send will come from the requirement document as well. So how in the requirement document it will be written what to test, how to test. Like I am expecting a range from A to Z or A to D or A to F. So those things should be written in the requirement document. I will read the requirement document and I will send those values and I will note down the values not manually in some software. I will note down and I will mark the test case as pass or fail. So in this case, when the number is like A to G or A to D, so the numbers are less. Think of a situation where millions of data points need to be evaluated. At that point of time, we need a automation interface which sits above the control disk and sends signal to the control disk in an automated manner. For example, I'm sending 200 values. So if I will use control disk, what I need to do, I will send one, then I will send two, I will send three, I will send four likewise. But in automation interface, what I need to do, I need to put those values in the automation framework. Then the automation framework will execute all those tests and it will note down the output and give me the response like pass or fail. So this is the importance of automation interface. So this is a very critical, I will say, part in the industry. So anyone who can work in this automation part, he could be an asset to the industry. So you can think of how you can bring automation to the work that you are doing currently. So that will help you in a very greater extent. Now, as I said, the inverter issue. So these are some basic building blocks, software building blocks of the inverter issue, like bootloader, center sensor interface, motor control algorithm, safety fault management, communication stack, diagnostic. All those things are uh, a part of uh, the inverter software. So bootloader is like, as we, let us say, we bring a new laptop, there is OS already installed in the laptop. You could think of bootloader as the OS of the software. Above that, we install MATLAB, we install Typhoon Hill or many things. So those are application layer. Okay, the user access the application layer, not the base layer. Okay, so diagnostic is about, let us say, you let us say you have a fault in the engine. You could see some signal in your dashboard, that is a part of a diagnostics. Okay, and then motor control is not visible to us. And here I would like to make a statement that diagnostic is being implemented almost all of the in all of the parts, which is safety critical and which is required. So when you go to a servicing center, you see a engineer comes with a laptop and connects your OBD port and diagnose something that is being done by that is called diagnostics. And he basically reads the vehicle data with some codes like 22. Something is called as read by identifier, something is called by write by identifier. So he does all those stuffs, and those are being saved in the memory so that he knows what trouble is there in the vehicle. Let us say you drive in the modern vehicle, the driving pattern is also being recorded in some of the vehicles. So if you drive harshly and you go to a shop and you say, no, I was driving calmly, so the engineer could find out that you drive at this speed at this point of time. So that accuracy he can see from your vehicle logs. That is possible in the current vehicle. Now come to the system level example. Okay, so for the system level testing, the word system is different for component manufacturer, different for vehicle manufacturer. So in system level, basically, we do PHIL testing or hill testing, thermal management testing. So normal hardware here is DSpace, NI, Opel RT systems, or any hardware you could think of, hardware in the loop system. So the um, adoption of the hardware totally depends on the project requirement, nothing else. Like DSpace does this well, or Typhoon does that well. You normally those things are not being considered here, because almost all the, what I can say, almost all of the functionality is defined. Like let us say if I want to test a component, I will go mostly for DSpace or Typhoon HIL. If I'll go for uh, vehicle level testing, I will go for some Canoe or Vector. Uh, I would say these are preferable, but it is not that we cannot do vice versa. We can do. So now, as I said, the system testing is a big word. So there are different type of system, like body system. body subsystem bench, powertrain, infotainment, ADAS, network, and harness. So the the system bench in this domain do test most of the functionality within that subsystem. Like the power system bench will, a powertrain bench will test all the functionality related to powertrain. The infotainment will, subsystem bench will test all the things, almost all the things related to infotainment bench. So some test cannot be performed on the benches which required a dynamic testing. For example, let us say when the vehicle speed is greater than 40 kilometers per hour, the volume will go up. This is very tough. This test is very tough in the lab condition. So we need to test that in dynamic testing. It is not that we cannot test, we can test, but there are some preferences as well. Now, the figure that you are seeing uh, is sits above the subsystem bench. When one subsystem bench, when the subsystem bench tests are being done, then we go for the lab car. Here, mostly you can see the wheels are not touching the ground, or the axle normally are being disconnected from the wheels due to the safety concern, but most of the things are functional in a lab car. Okay, the lab car, uh, the system level testing that we do with lab car, with almost all of the issues present. Let us say some issue are not available, we do simulate that issue with some simulation software. Then in this stage, to test the functionalities, uh, the in this prototype stage, we do a large alteration in the harness itself. For example, let us say I want to inject a fault. So how can I do it? So I want to inject high voltage fault in some ECU1. So what I need to do, I need to disconnect that um, power line. I need to connect it to some high voltage that is being written in the requirement document. So I need to do that. So for that, I need to manipulate the harness. I need to do some alterations to the harness. So in this stage, all the alterations are allowed, and we do a lot of alteration in the harness for testing purpose, with the testing purpose, and that is being defined in the test is defined in the requirement document. Okay. So in this stage, the vehicle could be interfaced with some vector hardware for testing. The ECUs are still in development stage. So we need to continuously we need to give feedback to the developer that these are the things that is not correct. That is, when I say not correct, that means it is not according to the requirement document. So we do give feedback through a software lifecycle management tool to the developer. So the developer will fix that, and he will create another patch of a software that we will again flash into our ECU and will test. So this iteration carries on. Then for EV powertrain, and this is true for IC vehicle as well. This is not only to the EVs. This is true for IC vehicle. For EV powertrain, we can have uh, we can have different type of simulators. For example, if you have a 540 or 60 volts or 700 volt battery pack. So in the initial stage, when your battery pack is not ready, but other functionalities are ready, what you can do is you can take a high voltage power supply, high voltage programmable power supply, and that could act and use some simulation, and that could act as a battery pack to your vehicle to check some of the critical functionality that is already being implemented in the vehicle, but uh, with some limitations as well. Then the replacement that I said, the primary battery could be replaced by a high voltage power supply, and the secondary battery as well could be replaced with a high voltage power supply with some additional simulation, simulated device. So to work in this environment, you need to have high voltage certification, else you are not allowed to enter into the premises. Now, when this testing, this lab car testing is done, and then we can start think of a vehicle testing. So when I say this testing is done, so this is not a first in first out type of testing. There is a possibility that all of the things works simultaneously. Simultaneously, I am developing, simultaneously, I am testing in iterations. So there are some methodologies like agile methodology where you develop the vehicle, you develop the software with in sprints like 2 weeks duration. In 2 weeks duration, you iteratively increase the functionality in the software. So don't think like one thing will over and another thing will start. So this was carried this first in first out was this type of development was is called river flow type development, which is time consuming, but currently we are not doing that. So currently, if you know, China is releasing new platform in every 2 years, that is 24 months. So which is like a engineering marvel, I can say. Why? Because normally prior 10 years or 7 8 years to develop a vehicle, it was taking at least 10 years. Okay. So why? Because the development of a new vehicle is very complex, but now it could be done within 24 months. So uh, uh, it is not achievable if we'll finish one thing then start next thing. Everything works simultaneously, development, testing. And when you do testing at very initial stage, you save a lot of cost. Why? Because initially you know that this is the fault in my software, so you correct that. You do not wait for 6 months to know, okay, this is the issue with my software. Now, let us, with that knowledge, let us come to the vehicle level testing. So simultaneously, iterations for vehicle will also be there. So all those things that is being tested on subsystem level or a lab car level will also be tested in the vehicle level. Okay. So in full vehicle validation, we do validate everything that is comes under safety or that is related to performance, range, acceleration, durability, NBH, EMC, crash, fire, everything is being tested. Okay. Then to test all of these things, we need to have some standards, some regulations. Okay, so uh, take an example of a normal vehicle with some ADAS level, let us say 2. If uh, if you have a vehicle with ADAS level 2, which has ADAS level 2 or 3, which has dynamic braking, and uh, maybe you drive it in a very crowded place, and suddenly someone comes in front of you and your safety is activated, then you will see your vehicle will apply sudden brake. Has anyone faced that in the vehicle? Okay, so in some uh, vehicles, what you'll see, there are two type of ADAS. One is camera based ADAS, and another is sensor based ADAS. And some vehicle have sensors and camera both. So in this ADAS labels, when dynamic uh, cruise, you can say, or those features are activated, and someone suddenly comes in front of you or beneath you with beyond the predefined distance, either braking action will be carried out, or you will get a you will get an alarm or something like that. But think of this situation in India. This is very common, right? So our roads are normally little bit congested, and the for that reason there could be a false alarm as well. Think of a situation where you are going in a vehicle with cruise set to 120 or 150, and sudden out of nowhere, suddenly some vehicles or something breaks. Okay, and you have set this ADAS level to sensitive. Then what happens? A sudden, as it is a D level, it is the highest priority, your vehicle will brake in a very what I can say, within no seconds, within very limited, like 10 to 20, in 10 millisecond, it will start reacting. So, and the person behind you don't have any ADAS in his vehicle. So what will happen? He will bump to your vehicle. So that is a safety hazard, right? So we need to find out how this safety hazards could be minimized. To for minimization of this safety hazards, okay, we need to first identify how much severe the hazard is, how we are exposing ourselves to that, how often we are exposing that ourselves to that situation, and can we control that? So these are the three basic questions that we need to ask prior identifying the potential hazards. So maybe uh, from the audience, can someone tell me uh, what component of the vehicle you think, if fails, creates a destructive effect to ourselves or the pedestrian or someone present in the vehicle? Can you tell me what are the components in the vehicle, or you can name them?
Sir, the
Brakes,
battery.
Yes, battery could be there. Break could be there.
So the
Okay.
control unit module,
Ma'am, which control unit you are saying?
ECU.
Okay, so there are different kinds of issue. For example, I have a light issue. I have a issue related to ADAS system. I have a issue related to braking system. Okay, so there are different kinds of issue. So depending on how critical the issue is or how critical that component is will decide like how important that component is to our vehicle or how much that component can contribute to the hazardous effect. Correct? For example, if my uh, turn indicator fails and if there is a, let us say, hazard level A, and my ambient lighting fails, so both are lights, both, let us say, comes from for example, we are considering comes from a same ECU, but the effect when turn light fails and ambient light fails are very different. Correct? So we need to categorize all those things. How we do that? By asking these three questions. So now my screen is visible now.
Yes, sir.
Yes, sir.
Visual.
Okay, fine. So let us take an example from this for the same inverter. Uh, we are cruising at some 120 kilometer speed with cruise on, and suddenly there is some issue with hardware issue with our inverter. Okay, so what we expect at that moment? So there could be some devastating effect. Okay, so we need
Excuse me,
to
sir.
yeah.
Sir, screen is still showing standards and regulations.
Standards. Yeah, it's standards or regulation only. I was just explaining the S, E, and C. Yeah,
Okay, fine, fine, sir.
fine. So we're cruising at 120 kilometer speed, and suddenly our inverter fails. So what we expect is there shouldn't be any accident. The limp home mode should activate, and somehow we should manage to reach our destination. Okay, so that functionality is critical. Now, this criticality is being divided in four types: SLA, which is lowest safety level, SLB, SLC, and SLD. What matter most is the SLD level, where we can have life-threatening hazards to ourselves, and for SLA, the severity level is low. And for QM signals, the severity, there is no safety critical requirements beyond standard quality process. Okay. So like I said, the side light could be some safety critical, and the inverter could be a safety critical. The ADAS system could be a safety critical. But if your mirror is not working fine, the I'm not talking about the side mirror. I am talking about the, let us say, ORVMs not working fine, then that will not pose that high amount of issue. So how this SL uh, is decided? So we use this table where we categorize everything like, can we control it? How much we can control it? How many times we are being exposed to that environment or condition? So taking all of this, we find out the ASIL level of that particular component. So where A is medium, A is minimum, and D is maximum, and QM doesn't pose any issue. Now, testing infrastructure and tool. I have already explained the testing infrastructure, that is DSpace, and how those things are being connected and how we test. So this is the view where you can test a drivetrain system. Okay, so the ECU test is a software which is used for the automation, and vector, similar to DSpace, we have vector as well. So emerging trends. So currently, if you can do one of these, you can be like in top 1%, like AI based testing, predictive fault detection. For example, if your vehicle have 5 buses, like powertrain can or chassis can, and you are collecting data from all of the ECUs. Okay, and through gateway you are collecting those data, and you are training a AI model. And you are predicting the cause of the fault, or when you need to go to the uh, servicing center. Those could be like very useful. Then digital twin, I have already explained about the example, like a square and all those things, and that is a digital uh, twin of a control logic. Similarly, you can have a digital twin of a motor or a inverter. Then solid state battery testing, then recycling testing, sustainability. Now comes to when it comes to sustainability, the things that you are doing, how much sustain they are. I mean, how far you can go with them. Basically, those things comes under sustainability. Then vehicle gate. Okay, when I have shown you this image where vehicle bus 1, vehicle bus 2, vehicle bus 3, and vehicle bus n. I mean, when I say that, I mean in the vehicle, you have this kind of issue arrangement where can 1, can 2, and can FD3, this kind of different, what I can say, uh, different channels are present. To those different channels, different issues are connected, and those if issues share data with the vehicle control unit with the help of vehicle gateway. So this vehicle gateway manages all the data from the different issues that is present in the vehicle. And in the modern vehicle, there could be minimum 50 to 55, minimum 50 to 55 issues. Now, uh, I have given you example of the inverter. Similarly, we could have a battery thermal runaway test and BMS hill testing. So in battery thermal runaway, simulated overheating of lithium ion cell. So we need not uh, do overheating of lithium ion cell. Let us say we have digital twin, then we will have thermal component. We will simulate heat in those component, and we can test that. So while doing this, BMS will respond. The BMS will think like the heating is actually being done. Why? Because BMS will receive the signal from the BMU that this cell is being heated. Okay, that cannot differentiate between a real signal and a simulated signal from a digital twin. Then in BMS hill testing, real BMS is connected to simulated battery system. I have already said, if you are making digital twin of a battery in the initial stage of your development, you can have this kind of arrangement. Then in the testing, I have explained, like in a lab car, we need to how we alter the wiring harness and inject high voltage fault. Then some challenges in the EV testing: high cost, definitely infrastructure demand. The way I am explaining these things seems very easy, but these are very complex tests, and what I can say, it takes so much of time and patience to learn all of these things. Then some of the extreme tests cannot be done in India. Then battery degradation prediction accuracy, it is a very what I can say common issue. Then last but not the least, need for trained manpower. Main challenge is like we need to have trained manpower for this. These are some of the key challenges that we face, and example scenario, then some of the solution and its impact. Okay, now, so uh, what I can say is like these are some of the evolving areas in my understanding for research and academic opportunities. That is battery degradation modeling, fast charging impact analysis, BMS algorithm, AI for fault detection, digital twin and simulation model development, software defined vehicle. Here, I'm repetitively explaining like we do have more than 55 and 60 ASUs or even more than that. But in some very sophisticated vehicles, there could be zonal architecture. You need not have 60 ECUs, just you need to have four or two ECUs, which divides the vehicle in zone wise, and which will perform everything. Just we need to throw the software and the functionality will be activated. Why? Because the hardware is already present. We called it high performance computing, HPC, which is present inside the vehicle. Okay, so which is a soft, in that way software defined vehicle is a evolving topic. And if someone could work on this specific this two topics like software defined vehicle and digital twin, like it is it sells like a hot cake in current scenario. Then EV testing ensure performance, safety hazards, and reliability. And you need to do that in component level, system level, and vehicle level. Also, you have some global or uh, national compliances that you need to meet to run your vehicle on the road. So we need to do that as well. That is called homologation. Then current trends like AI driven strategies, AI driven technology that I have told. Then digital twin, automation, I have already explained. Then these are some of the things where you can solve a problem and you can go for a collaboration with any of the, what I can say, industry. Like I have solved this problem, we can collaborate on this. This kind of thing can also be done. That's all from my side. If you have any questions, so you can ask.
Participants may unmute their mic and ask if they have any question.
Sir,
Hello,
what are
sir.
the most type of inverters used in EV, sir?
Sorry.
Most type of inverters used in EV.
Okay. So it is very generic question, but I will explain you. Uh, the type of inverter is solely depends on various factors. Like if you are a drive, you want to put that inverter into SUV, uh, the type of inverter will be different. If you put that inverter into a sedan, the type of inverter and the selection of the component will be different. So most of the inverters that is being used are patented, and no one reveals the what I can say, the actual technical specs of the inverter. But I can tell you, think think of a situation. Uh, I know a vehicle. Due to confidentiality, I cannot name the vehicle. I have worked on a vehicle where the rear wheel is being powered by a BJT and the front wheel is powered by a MOSFET. That I can say. So it totally depends on the requirement what you have.
Okay.
You yes.
Okay, sir.
Hello,
So
sir.
it's not specifically about the type of power devices, sir. Either it's a multi-level inverter or voltage source inverter. In that type, I asked this, sir.
Okay. Okay. So that is also not revealed anywhere.
Okay. Okay, sir.
And here I would like to tell you, like I know exact answer for this, but I cannot tell you.
Hello,
Oh,
sir.
okay,
Hello.
sir.
Yeah.
Hello.
Yes.
So how thermal management is done in the inverter, sir, nowadays?
Sorry.
By the thermal management of batteries.
Thermal management of.
Batteries.
Okay. The thermal management of battery. Could you be more specific about the thermal management of battery? Like the thermal management of battery is a huge, I can say, paradigm.
So in battery management system, for different algorithms we are using.
Okay.
So any specific algorithm is there. So for thermal management, the industry is using for.
Okay, ma'am. Initially, I have explained like for a same rating of a battery, the configuration of the battery could be different. So the thermal management, like the cooling, I can say it could be a water cooling or some proprietary cooling type. That is again depends on how battery is placed in your vehicle and where your battery is placed. So it is not fixed for any two type of vehicle.
Okay,
It
sir.
could be a uh, you could use water somewhere, oil somewhere, or somewhere. If it is a light vehicle, you may not need all those things. Just the fins will do the work.
So
Or
mainly
yeah,
the temperature sensors, isn't it, sir?
yeah, there will be temperature sensor in BMU, BM battery management in inside BMU. That is basic, but what I am saying is the temperature controlling mechanism could be different, and it depends on how much weight you are taking, how your vehicle is driving, like is it a front wheel drive or rear wheel drive or four wheel drive or all wheel drive. Okay, so it
Okay.
will depend on, it will vary on all those scenarios, even for
Hello.
same weight category.
Okay.
Yes.
Thank you.
Hello, sir.
Yeah.
Yeah, thanks for the session. Sir, my request is, can you suggest some references wherein students can get to know some of these things, some basic stuff, and they can start working on, let us say, algorithms, Python, use of Python, etc., so that they get some exposure and they will be ready for the future job market. Some simple projects, can you suggest?
The four things that I have suggested, the AI based AI based sorry, I forgot that word. Just give me a second. I will tell you.
Is it predictive?
Prediction. Yeah. Yes, the AI based prediction. So how you can do that is you can use multiple Raspberry Pi or that kind of low cost what I can say controllers, and you can simulate that controller in some DSpace or in MATLAB, and you can breeze that uh, vehicle which you have modeled into this what I can say into this controller cards, and you can record those data and you can train that. You can do that. The reference for all of these you will get from the websites like the OEM's website, or you can go for Magna's website, you can go for KPIT website, the solution provider basically. Okay, or you can go to Robert and Bosch website. You will see what uh, they're working on, what latest technologies, right? Then
Yes,
second
sir.
thing, you can go for you can work on simple electric machines. You make it like start from the differential equation of a electrical machine and gradually add non-linearities. Okay, so uh, although it seems a very basic, but you will surprised to know this is one of the hot topic in industry. The basic uh, uh, differential equation based take basic differential equation based model and add non-linearities to it. This could be a I can say a project. Then you can you should have basic know-how how the hills work, how real-time simulation work, how this real signal are being interfaced with the controller cards. So you can use a very cheap controller card and start all this.
Okay, sir. Okay. Yeah, thank you very much. And second thing is, can you briefly throw some light on software-defined vehicle because that is also one of the hot topics across the board.
Yeah. So currently I am not working on software defined vehicle. So I won't be able to tell you the exact specification, but what I can tell you is like it is a hot topic. It is doable, like with the help of this low cost controller cards. How you will do, you can generate Python, you can have Python codes for all the ECUs. I won't say ECU, all the controllers, and you take this controller as a zonal controller. I mean, as a HPC, and you can start performing small functionalities on that. And uh, this is for all. I would like to tell that whenever you are doing anything, any simulation or any experiment, try to use a standard communication protocol, which is very essential. What we do in our research is like in MATLAB, let us say, we use go to or from block and directly we like start simulating. But normally in industry, we don't do pin to pin connection. uh, Mostly we use either CAN, LEAN, or some sort of communication protocol. So coming to your answer, you can start exploring with the low cost controller cards and start implementing small functionalities, and gradually you enhance those what I can say functionality. For example, if you are first you are trying to control a motor in day one, in day two start what I can say control a different actuator. So and in that way you will learn how this incremental things are working. And this is, I guess, is the concept of software defined vehicle, where you have the controllers, you only only release the software and the functionality is being added to your vehicle.
Okay, yeah,
And
thank you very much, sir. Yeah.
regarding this, you can get information from all the suppliers website, whoever is working on HDV, software defined vehicle.
Okay, yeah, thank you, sir.
So one more question, sir. It is that hybrid energy storage system using battery and supercapacitor is a feasible solution.
Sorry,
Sorry, battery and supercapacitor combination for EVs. Is it a feasible solution?
I'm not getting your question, ma'am.
Sir, other than using battery alone, combination of battery and supercapacitor, hybrid energy storage system.
Okay,
Uh,
ma'am, I cannot comment on this because I have not worked on such combinations. That could be definitely a research topic, but
okay.
I don't have experience on such combinations.
Oh, okay. Fine.
So, sir, I am Prabhat Kumar Ranjan.
Hello, sir. Good evening.
Hi, am I audible?
Yes, yes, you are audible, sir. Loud and clear.
Sir, kindly tell me. So, if hardware is not available, then a simulation for power electronics converter in hill environment is possible.
Sir, when you say hardware is not available, that means which hardware is not available? Hill is available, I guess.
Yes, hill is available in my
Okay.
computer. So I want to simulate any power electronics converter with a Typhoon Hill environment and MATLAB environments. So is there will be any difference regarding these two kind of simulations?
So if you are asking about the accuracy,
Yes, accuracy.
okay. So definitely I will say accuracy will be different for sure. It actually accuracy depends on the solver that we are using to solve the differential equation that we have made. So you can uh, check for the solver which is more accurate to your system. For power electronics, uh, you can say Typhoon Hill has some advantage if you are making a controller for sure. I
Yes,
will not deny that the tool chain of MATLAB like overpowers everything, but I would definitely say it adds some convenience. Typhoon Hill adds some convenience in the form of high fidelity models for sure. You will get some advantage on that for sure.
okay. Okay. It means it depends on solver.
Definitely. If you are simulating it offline, which solver you are using for solving the differential equation is important. If you
Okay.
have a hill, then definitely you need to go for the uh, simulators for sure.
Yes. And if there will be any hardware, then will be better with the Typhoon Hill simulations for interconnecting the our simulation results and the hardware results.
If you want to connect the simulations, like real-time simulation with your
Yes,
hardware, you
hardware.
there are certain things that you need to consider. For example, you could take the uh, firing pulses from outside, like it is a CHIL mode, or you can directly run it in real-time simulation mode without taking any signal from outside. So if you go for the CHIL mode, the accuracy for your simulation will be definitely better, and
Better.
you can use the hill simulator for rapid control prototyping, but I will not suggest if you don't have in-depth knowledge in rapid control prototyping. Why? Because your sensors need to directly interface with the real-time simulator, which is like very costly. And if your sensor somehow malfunctions, your simulator could be spoiled.
Okay. 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 Thank you. Thank you.
You are welcome, sir.
Any other questions from the participants?
Good evening, sir.
Good evening.
Sir, my question is about, sir, the variable charging rate. There are lots of fast charger has been introduced. What is the impact on the BMS due to this variable charging techniques?
Okay, so although I have not developed such system, but in the perspective of a tester, I can say, so when a system is being built, like this variable, what I can say, variable charger you are saying, correct? So the system is being designed for certain kind of certain range of battery capacity, and the battery can also take the current with certain rate, which is already fixed and controlled by the BMS. So when you charge it with when we charge the battery with variation in charging rate, definitely the BMS will not, the BMS will take the will not what I can say, the BMS will not um, BMS will not allow to cause any adverse effect within the rated capacity, within the rated range. But if you charge in the rate of charge is very high for most of the time, your battery aging could fasten. I mean, you could use that battery for, like, the life expectancy could be lower. Why? Because the life, it only depends on the life cycle, right? How much time you are charging it and how you are charging it. How if you are charging it very fast, the thermal management will work fine. With aging, the thermal management capacity, if decreases, it will cause adverse effect to the cell and later your battery pack.
Okay, thank you, sir. Sir, one more question I am having. We are having a battery management system for battery, and do you think in electric vehicles the motor also requires some kind of things like a battery management system, because there is a variable current coming input as an input in a motor, so it is also getting heated. Uh, the motor
I
get heated up. So
Okay.
do you think it also requires some kind of management system for motor?
I didn't get your question. You are asking if motor needs a management system, motor management system, we are saying?
Yes, sir. Yes, sir.
Definitely, motor has a controller, right? So all these things are being taken care of that by that controller, motor controller, so that it will not heat up. It will, like, it will work under its nameplate. So there are motor controllers. I have explained in the section where in inverters we have a section of electric drives and electric motors. in those sections, we do take care of all the uh, uh, what I can say, all the signals that is responsible for motor, which is originated or being influenced by the inverter. So definitely those sections are present in all the high performance EVs and in the lower EVs as well. That could be a part of inverter. Yes, but it is present.
Thank you, sir.
Welcome. Manish, are you asking a question?
Good afternoon. Good evening, sir.
Good evening.
Actually, sir, I have an issue regarding EV cars, right? So, my question is regarding why these EV cars are burning, means it is catching fire. So, my issue is regarding that. Why this car is means taking easily catching fire. Even if we see Ola bikes,
So
that too,
there could be multiple reasons. There could be
yeah.
multiple reasons for this fire. Some could be like software glitch. Some could be a software glitch. Some could be a hardware glitch. So is it depends like for a different vehicle, it could vary. It could happen that there is some glitch in software and the BMS couldn't balance the cells while charging it or while discharging it, and the battery pack catches fire. That's for sure. That could be a cause. Or for example, with aging, the the aging effect is not properly taken care by BMU. That could also be a cause for fire, or failure of communication could also be a cause of fire. So the cause of fire could vary.
Yes, sir. I have seen many Ola bikes catching fire
Definitely,
easily.
I cannot tell the reason, because for the Ola bike itself, there could be different cause which we don't know. That could be due to mishandle of the vehicle as well. We don't know, but these are some of the reason that I know could be cause to a fire. There could be some more reasons.
Thank you, sir.
You are welcome.
Thank you, Saurav sir, for such a detailed and informative session. Um, the next session, if you wish, we can take a break of maybe 5 minutes.
Okay. Can we take a break for 10 minutes maybe?
Yeah, sure, sir. Sure, sir. We can start from at 8:15 also, sir.
Yeah, that sounds good for me.
Okay, sir. Okay, participants, we will again resume at 8:15. So don't disconnect. Be connected. The next session will commence at 8:15 again.
Yes, and if someone have the uh, Typhoon Hill ready into their system, make sure it is up and running. Maybe you can do with simultaneously with me, or you can explore the things that I will be explaining with me.
Okay, okay, sir.
Okay. Thank you.
Hello. Am I audible?
Hello.
Hello, Saurav sir.
Hello. Deep Shekhar sir, when the next session is start?
Ma'am, it will start just in few minutes, ma'am. 2-3
Okay,
minutes
thank
more.
you.
Hello, Saurav sir. Saurav sir, am I audible?
Yes, sir, you are audible.
Okay, sir. Okay.
So, can I start now?
Yes, sir. So we can start with the next session. So participants, we will be starting with this next session by Saurav Sahu sir, which will be on introduction to real-time simulation environments using HIL. So I request Saurav sir to kindly start with the hands-on introduction of Typhoon Hill.
Okay. So currently I'm not able to see the charts, but can you tell me if there is someone who will will start working along with me, or just I need to do it by myself? Is there someone like that?
Sir, I have Typhoon Hill installed on my system.
Okay.
So I will try to follow you, but
Okay.
my system has a little bit of lagging. Maybe it will be working
Okay.
intermittently, but I will try to follow you.
Okay, fine. So in that case, so I will be
Any
explaining
other
the.
participant who has installed already has Typhoon Hill or has tried to follow the process that we shared today in the during the day?
Hello,
Okay,
sir.
sir, you can.
Yes, sir. I have tried and I have successfully installed the Typhoon software on my computer, sir. So I'll follow with the sir.
Okay, thank you very
Okay.
much, sir. Thank you, sir.
Thank you. So then just when I will go through the sections, just you need to go through, and when I will drag drop the system, you can drag drop the only just you need to drag drop the components from the library if it is possible. Okay, if not, no problem. So Deep sir, so how it should be like, shall we develop a model from a scratch, or we should go for a models that is already available in the library?
I think, sir, if a brief introduction is given about the means where everybody can find the components,
Okay, okay,
and then we can go directly to a already existing model.
okay. Fine, sir. We'll do that way only.
Okay, sir.
Okay. So let me know when my screen is visible to you. Is Typhoon Hill Control Center is visible to you?
Yes.
Okay. So when you will double click on the icon, this pop-up will come up. So prior to that, I would like to talk for 2 minutes regarding Typhoon Hill. So in Typhoon Hill tool chain, it has the software and hardware. Both are being developed by Typhoon Hill, which I think a USP for this in a Typhoon Hill environment. So you have various kind of simulators in Typhoon Hill environment, like 6 series, 4 series. I have worked on both 4 series, 6 series, and you will have different kind of facilities on 6 series and 4 series, like 604, 404. Previously it was 402. Then now you will have some virtual hill. uh, Anyone who don't have that one, that real hardware, he can do the simulation in Typhoon Hill as well. But definitely it is a simulation. Someone has asked me that question. I would like to tell that definitely it is a simulation only, but if you have hardware, definitely it is an advantage. Okay, so they have different kind of hardware that I will show you right now. Mainly the hardwares are differed with IO pins, then with different communication protocol, with different capacity of processing, with different kind of what I can say, you can go to certain time state with some specific kind of real-time simulators. So the real-time simulator could be used in parallel. Like if you have two real-time simulators, then you can parallel them and you can use them. So there is a upper cap for that. Currently, I don't remember the number, but mostly it is 16. You can check it in their website. Uh, the number of system that could be parallel. So they also do provide you different kind of power supply. If you have some tailor-made requirement, they do that for you, or else you can purchase different kind of uh, supplies or what I can say, power simulators for simulate your power in 4 quadrants. So you call it as power amplifier. You can buy a power amplifier and directly you can connect that power amplifier to the real-time simulator. In Typhoon HIL, you will get some high fidelity model which is already present in the library itself, uh, which will give you better accuracy if you run it in real-time mode with the with connecting a real-time simulator, definitely. So these are some of the basic that we should know. And I would like to tell you that the coding, the for coding, you but you use Python in Typhoon HIL. as the base language for all the codings that you do in by Typhoon Hill. Okay, then let us start exploring this Typhoon Hill control center. In the left hand side, you can see the device manager. Let us click on that. When uh, you can see the screen, please acknowledge.
Yes, sir.
Yeah. So in the left hand side, you can see the active hill setup. If my system would have been connected to a, real-time simulator, you could have see those real-time simulators name over here. But as my system is not connected to any real-time simulator, you will not see any real-time simulator over here. You can directly connect the real-time simulator. I think it has a type B USB type B cable in the back side. You can power it up and connect the type B cable with your USB drive USB put in your laptop. Then you should be able to see the name of you should able to see the name of the hill device. Could be a 4 series or 6 series, is irrespective of that. Then here the icons used for refreshing, and here you will this is for connection of the real-time simulator. Then these are used for firmware configuration. For every software update you get, and software update you get, you need to update the firmware in your real-time simulator. For example, I'm using excuse me, I'm using version 25.4 Typhoon HIL. If my system, if in the hardware, the firmware is of 2025.1, then my model will not be compiled in my system. So for that reason, I need to first update my firmware. So these things are done over here. Then let us come to the examples. When you click on the examples, you'll have a list of examples that is already present in the library. You can open any of them and you can simulate them and you can see the results. Okay, so you have aerospace, automotive, electrical circuit, battery management system, communication protocol, electrical drives. For some communication protocol, for most of the communication protocol, rather, I would say, uh, you need to have a real-time simulator connected to your device, else the communication protocol will not work. This library model will not work. If there is some requirement like this, you need to have a real-time simulator. Those will be written on the schematic itself. So you would get to know that, yes, I need to have this kind of simulator. Then electrical drives, general power electronics, and grid connected converters. So you can find all type of converters over here. So when it is written as grid connected converters, these are the example of grid connected converters. Okay, not the basic component. The basic component you will get in the library itself. Fine. Then hardware in the loop. In this section, you will get to know how the HIL works when you have a real hill with you. This is
Slides is not moving forward.
I'm not showing you the slides.
Okay.
I have opened the app and I am showing you
Yes.
the tabs. Is it visible?
Yes. Yes. Okay. Yes, sir. It is visible.
Yeah. Thank
Okay.
you.
Thank you.
Then in this three
Hello, sir.
uh,
Actually, it is not visible, sir. Your only Typhoon HIL control center is visible. The next part that
in
you
the
have
left
clicked
hand
on
side,
no,
I am highlighting the things.
no, sir. You
Isn't
only your cursor is moving, but nothing is visible there Only HIL control center is visible, I think.
Yes, sir.
Is
We are
this
able to see only that schematic editor, Hill SCADA, Typhoon Test ID. That's all. That pop-up window, the
okay?
first one.
Okay, okay. Just let me reshare it once again. Let me know when it is visible. Is it visible now?
Yes, sir. A three-phase grid-connected inverter PQ control.
Yeah, correct.
That thing, and left side we have.
Yeah, yeah. Okay.
Okay.
So, okay, I will start again. Then this hardware in loop library will show you how your hardware in loop works. If hardware in the loop works, if you connect a real-time simulator, then this shows how your CHIL works with Texas Instruments card. For that, you need to have a library. We need to have a Texas Instrument card, which is being provided by Typhoon HIL. When you buy Typhoon HIL, if you ask them, they will provide you with this card if that comes with their package. Then how to examples you can see how like how these things are being done, like boost, closed loop, C function, all those things you can find out. Okay, how C functions are being made and how this controller is being developed, all those things you can find out. Then you also have a marine power system with you and shipboard power system with you as well. So, in order to run them in real-time mode, you need to have that much of hardware capacity. For example, let us say I want to drive this marine power system, then my real-time simulator should able to handle this non-linear things. I mean, if the real-time simulator is capable of solving two machine differential equations and I am running three, then this model will not work. I need to have a machine which can run three machine differential equations. So that needs to be taken care of. Then microgrid. In microgrid, you will have different converters and energy storage devices. You can directly take them and run them, and you can see how the things are working. Fine. Then let's come. Okay, fine. In power quality as well, then power supplies. Yes. So these are some basic basic models that you can see, and you should run some of these things so that you will know how this environment works. Okay, so for power system guys, IEEE 33 bus system 13 and IEEE 4 is also there. Okay, so you can refer the IEEE document, and so that you have a greater understanding for that. I have worked on these two systems, 13 and 33. So that works fine. And but you need to if you are integrating it with any renewables, you need to optimize your system to a very greater extent. So normally if I'll add some renewables, this system may not works in 602 plus, or definitely not in 402. So you need to optimize your model for that. Then railway, also you will have some railway related things with you. Okay, fine. So now let's dive into the help. So let us say you are facing any issue. So you can refer the help and directly go to the documentation, and you can start what I can say, reading the documentation, so that you will have a better understanding. Then comes HL Academy. If you'll in the morning itself, I think Dr. Sonal or Dr. Acharya has provided you with a link. You go through that, and there is a HL Academy. You can do the Hill Expert course. It is free of cost, and you will learn a lot of thing over there. They have different sections for power electronics, for power system, for communications. All those things are clearly mentioned, so you can do that certification as well. So I will suggest everyone to go to that Hill Academy and do the certification course. Now comes the software. So if you have used a MATLAB, it's the same as the schematic is same as the our workspace over there. This is the extra thing that Hill SCADA. So this is being used to monitor the output and give input to the models that we build. So this has some similarity with this part. Schematic editor and Hill SCADA in offline mode has also some similarity with configuration disk. Like in configuration disk, we need to configure the model and compile the model to generate the HDF. Similarly, in this Typhoon HIL, we need to compile and load the model to the Hill SCADA, which is similar to DSpace, I will say. Then signal waveform generator, you can generate a waveform which you can use in your model, or you can collect the data and use some signal generator, hardware signal generator, and you can use it anywhere you like. So you, if you have a detailed PV profile with you, you can take that, or if you have data of that, you can also take the data. Then if you have if you want to generate a signal which is not defined anywhere, you have the data points, then you can take the data points and you can generate a signal over here, and you can use that signal in your simulation. Okay, then it is a signal analyzer which is also present in what I can say, MATLAB. Here you need to import that signal which you have saved, and then you can have its FFT and all. And then LUT extraction tool. So let us say you have an image, you want to extract the image from the image point, you want to extract the data, you can use this tool. Then testing and calibration. For example, you have your hill and you have some interface board, and you need to do the you have used that board for certain amount of some certain period of time. Then you need to calibrate that board. Then you can use this facility test and calibration. And in Typhoon IDE, you can automate your test cases. I have not used this IDE extensively, but if you know Python, you can use it easily. No issue with that. Okay. So I have not used it extensively, but it works on Python 3. Here you can see, you can take the embedded Python which is installed with this system, or system Python also you can take. You need to explore it a little bit. So the idea for this presentation is to tell you about the whereabouts about the software, and some basic idea about the modeling. Okay. So let us start the schematic editor. By single click on the schematic editor, you can start the modeling. Just give me a second. I will reshare my screen. Let me know if it is visible.
Visible, sir.
Yeah. So from here you can start modeling. Just click on File, New Model. Click on that. So I was explaining about the type of hill that you have. So if you click over here, you will see hill 100, hill 101, 402, 404, 506, 602 plus, and virtual hill. Virtual hill when we need not, let us say you just want to have a pure simulation, you don't have any intention to run that simulation in real time, then you could go for a VHIL. But if you are serious about your modeling, I would say you choose from any of this and start modeling. Why? Because when you choose any of the hardwares, you bind yourself with some real time restriction, which is good for real time modeling. So let us say I am clicking 402, then here hardware
Excuse
configuration.
me, sir.
Yeah.
Sir, does that mean that when we are using VHIL,
Mm-hmm.
so it means the model of those components will not be of high fidelity,
Yes,
or maybe there
that's
will be
correct.
some more approximations and assumptions.
Correct, sir. So
Okay.
I would give
Okay.
you an example over here. Let us say you want to you have a Hill 602 plus in your lab, right? So you want to use that and you want to run some model. Okay. So you have started modeling with VHIL. So when you will use the VHIL and drag and drop the models and you simulate. The environment will not take into consideration environment will not take the TS into the consideration extensively. Means let us say you have some timing issue with the different components, the VHL will ignore that at some point of time, which is not critical. Those all will be ignored. But if you are selecting, let us say 602 or 402, those things cannot be ignored. The uh, sampling time should be an integral multiple of like the sampling time that you have given in the model itself. So those things will be automatically taken care of when you select a device rather than a
Okay.
VHIL.
Okay. Okay, sir.
Yes. Then and then come to the device table. Just click on that on the device table, then you will get to know the power of your real-time simulator, what you can do with your real-time simulator. Let us say I am clicking on 402, what I can do. So 402 have for configuration 1, it have 3 standard processing cores. For configuration 2, 4, and likewise for DC-DC converter solvers for configuration 1, I don't have any DC-DC converter solvers. Okay, so any of this configuration, if I'll choose, I don't have a DC-DC converter solver. That means in 402, if I want to have a research on DC-DC converters, which is not a mathematical one, which is a high fidelity model, which then the 402 in 402 that thing cannot be done. It shows that. Okay. If you have a mathematical model and you have manually added fidelity to it, then you can do that for sure, but not from the library itself. Okay. Then signal generator for all the configuration, you can select 10 signal generators. Okay. If you have if you need to have PWM analyzer, you can use 4 of them if you are selecting configuration 1. Okay. So these are the basic things that you should have in your mind when you are modeling in Typhoon HIL when you are modeling typhoon nature, that too if you are using a real hardware for high fidelity. Okay, so let us say you want to I want to know from the audience, if you want to simulate a machine, then tell me which configuration you should choose. Let us say I have uh, two machines. Which configuration should I choose? Can anyone tell me by looking into the table?
Configuration 5.
Yes, correct. So let us say my I am simulating a 5-bus system. In my 5-bus system, there are two machines. That could be anything. Then I should select the configuration 5. Then my simulation can my environment can compile my model. So I will select that from here. Okay. Simply I will click on this. Okay, so then comes to simulation method. You can choose any of this. Then simulation time. Normally you keep it in auto. If you know exact timing, then select one, or else keep it in auto. Then if you know any specific thing, like which integration method you want, then you should select all, let it be. Then click on next. So here is the summary that we have done. Okay, then click on finish. So now all the libraries related to that configuration now will load to your environment. So just wait for a moment. Now here you can see a blank page. Now you can start modeling. So just for modeling, you need to drag and drop. When you drag and drop, you will see at some models, you will have a weight over here. I will just show you. Sorry. Can you see this? Weight for real-time simulation is equals to 1. It shows that this is a high fidelity model. Okay, so as I mentioned that we have selected a 402, and 402 has 4 cores. Okay, and in that 4 cores, the weight is limited. That means a single core can handle a certain amount of weight, which is being assigned to each of the devices, which is a high fidelity model. Our machine has a capacity, and which is measured in weights per core. So one core can handle some X amount of weight. Okay, so we need to, as a developer, as a researcher, we need to know the capability of our machine. Then we need to calculate the weight for that, and then we can start simulating. I mean, we can start modeling. Correct? Okay. So this is the thing which is critical, and everyone should know this. Okay. Now let us take this simple example. Okay. Oh, no, I will just give me a second. Just an input switch. Okay. So in the presentation, someone has asked like how to do the CHL and all those things. So if I'm just talking this in the context of inverters, as it is for EV. So let us say you select digital input per switch. or digital input per leg. This means when you select this configuration, you can have the uh, PWM you can take the PWM input from this many from this what I can say number pin number 1, pin number 2, pin number 3, and pin number 4. There are 32 pin. You can see there are 32 pins. I can choose any of them, but I cannot choose same pin twice. Okay, so I can take any PWM signal. Definitely that should lie within the capacity of the real-time simulator. Then I can generate a PWM outside and take that PWM with the help of these pins into my simulation and start simulating. And this will called as controller hardware in loop simulation. Why? Your controller is outside, right? Okay, then let's start modeling something really what I can say simple. Just I will show you. Let's take it constant. Okay. Why I am doing this? Because I want to show you like how these things works. I will compile a different model. Just you need to know how things are working. Okay. Then let us take a voltage measurement. Let's take an inductor. Let's take a capacitor. So you can add a register as well. No issue. Let's take a load. This thing. Let's take a voltage. So I guess I have finished. No. Okay. So the point here that I want to make is either you can directly give voltage from here, or you can give a variable over here and define that variable from here. So 5 volts. Okay. Or directly you can, if it is a value, take it, give it this value. You can do this as well. Okay. Fine. So now we can do for all. So the advantage over here is even if I give a constant value over here, I can change this value while the simulation is running and I can see the changes. So if I will use this as teaching, what I can say, if someone is uh, explaining basic power electronics, taking the power electronics course and explaining to the students that this could be a very useful tool to show the what I can say, normally we say like don't sort the same legs of an inverter. Those things you can easily show by this simple, what I can say, model. Okay. Now I will compile a model and I will show you how the things will happen. Controller design. So now I will go to file, then open a model. I will give the path over here. Then I will click on open, right? This thing is open. Now here is a basic control logic. Now here you can see lot of icons. Okay. This is the initialization panel, and here you can see compile and reload the model in VHL mode. Why VHL mode? Because my system is not connected to any real hardware now. Okay. So I will click on this. So when you click on that, you will see a lot of, sorry, you see a lot of processing over here. The machine is generating a code that I have explained, which is similar to DSpace configuration disk, right? If someone has worked on that, they could correlate now. So now this is, as I have choose the VHIL, the system is directly, the code is being directly loaded to virtual environment, which is being created in the same folder. If someone has any questions, they can shoot, no issue. So I have modeled a panel prior. If I don't have a panel, I can create one. I will show you that as well. So as I have a panel, I will click on that. Okay. First, I will show what I mean. Fine. So this is a panel, which is where we can see the, what I can say, the results. Okay. So I will show you different models for sure. No issue on that. So let us understand this panel. Okay. As we are, we have different components in the schematic here. What are the components? We have a power supply, right? We have some voltages, voltage measurement. We have a load. So when we go to the, what I can say, the SCADA hill, here we can take different widgets. For example, I want to put some values. So I will take a widget which will take the value. For that, we can use a knob. We can use a slider. We can use a text box. Anyone will work. What I need to do, just double click on that. Just double click on that. Go here, and what you want? You want to say this, like put this value, correct? Are you getting me? I will do it once again. Just double click on anything that you want to have. Go to edit in code editor, select that variable and click on insert. We'll have it over here, correct? Then you need to save it. Okay. So now it will be saved. No problem. Similarly, you can do over here also. Go to code editor, select the source. Why source? Because this is a source and its name is VS3. So we'll go to the Hill SCADA. Now we'll click here once and we'll put insert. will save it. Okay. So in this way, we can connect this knob, okay, this knob to my variable over there. Similarly, if I want to see a signal, what I can do? Just drag and drop the capture scope. It is showing that only one capture scope is allowed. Okay. Click on OK. Go to signal, add a signal over here, click on the drop down and select the signal that you want to see. For our case, it is VS3, the name of the signal. And we also need to click on the viewports. What does it mean? Let's see. Can you see the difference when I'm clicking it? Where I want to see that port. So like that. Okay. So let's delete this. Okay. Now, so in this way, you need to take the widgets and you can use it. If you want to log some data, you can take this data logger as well. Click on this. You need to define the format. For a MATLAB. You can choose .mat. You can have it CSV, any HDF5. These three formats are available. You can choose. Then you can choose the output directory as well where you want to save it. Then similarly, you need to add the signal over here. Click on the signal, click OK. When you start simulating, this will start saving the data. Okay. Now, let us go to this place. Okay. So I told you that this model will, let us say, take some model will take data from outside with some pin numbers, right? So here what you can do is, like, you can select the signal, which signal you want to take. Let us say the input signal is 10 volts, but you want to scale it. So you can add a scaling factor as well. Then if it is fixed, then you can lock it as well. So do anything. If you lock it, it will not change. This is for safety purpose. Okay. So why this is 16? Why this is vary from AO1 to AO16? Because I have chosen Hill 402. It has 16 analog output. Okay. Similarly, digital output also you can check. Okay, fine. So this is one model that I want to show. Let us go for another model. I would like to show. Okay, let's compile it. Why I am compiling multiple models? I want to show you how the process is being done. In the meantime, if you have any questions, you can shoot.
Sir,
Okay.
may I ask at this stage? May I ask at this stage?
Yeah, you can ask.
Sir, in this simulation diagram, if I want to put my any extra logic, extra code, then at what stage and where I will put my extra logic in this simulation model?
Here you can put, as I have shown you, a user-defined C function is there.
Yes,
So
yes.
there you can put your logic
Acha.
in the
Suppose I
schematic
want to
itself.
change this inverter with internal modulator.
Mhm.
Then at this point, may I change my logic?
Sorry, I didn't get your point.
Sir, this is written inverter with internal modulator, and if I want to put some extra logic code in this block and replace this code with my own code, then what will I do?
You need to have an inverter with controller design. For that, you need to do this. Go to the model, click on that, and if you click
Yes.
OK, you can have your own. Or if you have a controller and the controller is being interfaced to the hardware and the
Yes.
PWM is being generated over there, you can choose either any of this, like per switch or per leg. Then you can have your simulations, like you can have your control logic over there.
Okay. Okay. Thank you.
Okay, so when we load this panel, then here you see three icons. First is for model setting. For example, let us say I want to set the source voltage to some 0 volts. Okay, I want that. That is my initial condition. So when I put this 0 and save this model, the settings, that is 0, is being saved with the extension of model setting. Okay, so next time when I load this model, I just click on this and I just click on setting.runx and open it. All the things that I have done, like I have set the settings to 79 volts. Okay, so 79 is being saved. Okay, so this is how I can save my settings as well in the form of runx file. Here you can see the extension is runx. The extension of the SCADA is .cus. Okay, and I was explaining you like don't if you can take this and use this as a TLM instrument. Here you can sort this directly as there is no hardware connected, external hardware connected. Even you can do that in if you connect a simulator as well, no issue. So you can show the students like what happens when SA bottom and top do short circuit. Okay, those things you can do. Now let's simulate this. I do something that I don't know. For example, you can see the changes. Okay, this kind of things you can do and show to the students so that they understand the what I can say electronics in a better way. See, short circuited. This is what I mean. So now some more thing that I want to explain, like just a couple of minutes. So if someone is working on power system, they normally don't have this kind of small what I can say models. They do have large models. So to resolve that issue, you can use core coupling. Here you can use this type of core coupling for three-phase system, where your simulation will be divided in some segments and those can run on the real-time simulator. This will really helpful if you are a power system student, or if you simulate a multi-level inverter, or use a inverter with separate switches or DC-DC converter, then this will really help you. Then if you have multiple devices, then you can use device marker as well. Device partitioning, go to device partitioning, go to device marker. Let us say you have two devices, you can mark device number one, it starts counting starts from zero, device zero and device one. So in that way, a single simulation will work on two devices. If your what I can say, your controller or your simulation is very heavy, then you can use this to really helpful strategies like device. You can partition the same device. You can use multiple device at the same point of time, but uh, you should use six. If you are using a 602, then you should use a 602. If you are using 604, you should use a 604. 402 doesn't have the paralleling capacity. I need to check for 404. You can also check that as well. So this is the basic thing that I want to convey. If someone has any questions, they can ask me now.
Sir, I have a question. Sir, I have done simulation with this Typhoon Hill and MATLAB software also. Then what will be the any extra advantage or beauty with this Typhoon Hill software so that it will be compared with MATLAB? Any extra advantage with this Typhoon Hill software?
So you need to find out that advantage, like why you use a Typhoon HIL, that why you selected Typhoon HIL. You should know that, I guess. Like, is it due to some easy execution of the model, or it could be due to some easy execution of the model, or availability of the high fidelity, what I can say, high fidelity library models? Those could be the reasons.
Okay. And if I want to make a difference regarding the real time and normal MATLAB simulation runtime, is there any extra advantage of these waveforms in
I
both
didn't get your
software?
point. I didn't get your point.
Sir, if I have done a simulation with this Typhoon Hill and if I have done
Okay.
a simulation with MATLAB,
Okay.
then then all waveforms have come with these two software. So is
Okay.
there any extra advantage so that we can visualize by seeing that it is from Typhoon Hill and it is from the MATLAB?
I would say, if you are using some kind of hill and taking the data, so you will be taking that in a DSO, right? So if you're taking that in a DSO, no one can tell you that it is being taken from a Typhoon HIL or MATLAB based DSpace model. So it will not be a like it is it will not be known to anyone if you will not say that.
Oh,
And why the variation is there, that you need to find out. Like that could be
okay.
with due to anything, like any uh, variability due to modeling or selection of sampling time. If everything is matched, then I would say there could be a difference in fidelity. So due to that fidelity, you could have different results.
Okay. Okay. Thank you.
Yeah, welcome.
Sir, I have a related question. Means from this question, the question arises in my mind. Um, Sir, actually, I want to say that if I am developing a multi-level inverter, say in cascaded system with sinusoidal PWM in MATLAB, and the same
Okay.
system I'm trying to prototype in Typhoon. So,
Okay.
will the means if I keep the input as the same components with all the set values, so is
Okay.
there any difference in the simulation which I get? Means the
If you
output
are
which I
using
get, is there a difference?
a mathematical model, then no, you will get uh, no difference. If
No,
you are
with the
using
load
this,
forecasting model, if I'm using real-time data in that, if I embed it through AI, that the real-time data is to be fetched to this model,
Okay.
then which would be better? What would you suggest? Means should I go for MATLAB or should I integrate it with Typhoon?
That totally depends on your convenience, ma'am. So if you have a if I able to understand it correctly, if you have a weather forecast data anywhere in the network, and you are tapping that data into a simulation through any protocol, that could be a HTTP protocol or any protocol, then you are feeding that data to a model. Am I correct?
Correct, sir. Correct.
Okay. So if you are doing that, you should use a simulator, correct? Or else
Correct, sir.
how you will fetch the data? Okay. So if this is the case and you are using Typhoon HIL and DSpace for same level of fidelity, I don't think there will be any difference.
So according to you, both the simulations will yield the same output.
Yes, it should yield the same output.
And that would be same as replicated in the prototype, or there will be some losses?
When you say prototype, I didn't understand.
For example, if I implement the same model in a hardware.
Okay, so again, now it will depends on how much fidelity you achieved in your model. If you are in level 4, I would say there will be very minimal difference, which you cannot find out. Like with some very sophisticated machines, you can find out, right? So it really boils down to the theory that do you have a high fidelity model? If yes, then you can go for it, and there will be very minimal change, which is not considerable for sure.
So then for MATLAB, we do get actually a FFT transform ratio, correct? So can
Okay.
we fetch the same, the fast Fourier transform, can we fetch the same through Typhoon as well? If yes, what is the process?
You want to do FFT from Typhoon HIL?
Exactly.
Okay, so I have shown you a signal analyzer, right? So what you need to do is, ma'am, you need to have a signal in CSV form or in .mat form. Then you need to, for Typhoon HL, I guess you can import it in .csv form. Then you can directly apply FFT on that. And for me, I will tell there is an advantage. You can, as I have shown you the IDE, there you can integrate all Python libraries into Typhoon HIL. When I say you can integrate Python libraries like pandas and all those things, so it really becomes very powerful, which I don't know if DSpace supports, because I have not worked on that part of DSpace.
And that won't be requiring any API integration.
No, no API integration is required. You can go with the API present, that is IDE. You can do that, but I'm not sure up to which extent you can do that, but definitely you can do that. I have seen some of my colleagues doing that.
Okay, sir. I would have a small request to the organizers if the recording of this PPT can be just shared with us. Thank you, sir.
You're welcome, ma'am.
Good evening, Dr. Saurabh, sir.
Good evening, sir.
My one point of discussion is uh, why should we not go for just hardware implementation of a converter circuit for any application, why
Oh,
why we are more concerned about just simulation aspects? Either it will be from MATLAB or Typhoon Hill. Yeah, we are why we are more concerned uh, for simulations only. Why we are not testing with the real hardware? I think it would be more appropriate if we go for a real hardware circuit. What is your opinion?
okay. So there are two things involved. First, R&D, the know-how. We don't know every know-how when we're doing R&D. Point one. Point two, cost. And point three, safety and security. So when we consider the R&D part, we don't know how if we'll connect in certain fashion, like for multi-level inverter, we connect the switches in certain fashion. We don't know how the output will be. We can have mathematics on paper, but that is what these real-time simulations are doing more efficiently than us. This is the reason one why we are using saving time more efficient. Then reason two, when we are going for this hardwares, we need to have some cost. If you see that, for example, if the college, the BIT Mishra has purchased a simulator and the simulator runs for 10 years, let us say average 50 students work on that. If we'll accumulate all the cost of the hardware, that will be more than the simulator. So this is the thing. Third thing, the safety security. I cannot tell my guys to work on more than 12 volts and which they don't know, like they don't know how the system will react. So safety security is prime importance to us, right? So let us say I am simulating 800 volt inverters, then in my wildest imagination, I cannot think of doing that directly after mathematics in the books. First I will do the mathematics in the book, then I cannot think of, like I will go and assemble the hardwares. So these are the three main reasons that I could think of as of now, which could be best reasons for adopting the real-time simulations.
Right, right. It is very clear. It is very clear. That is very fine. But simulation platform should be limited because there are so many simulation platforms uh, that should be limited to the users. That should be appropriate one for particular application. I think so.
Definitely what you are saying is correct, sir. Like
Yes, sir.
let us say I'm taking the
Because
example of
yes. Because
this method.
it should be more confusing also because one users in one in confusion. I should use this or what. So that should be, I think, in my view. But I want to take your opinion.
Sir, if you see, if you deep dive into the roots, everything is being converted to the C codes only. The machine understands the binaries only. Either you take a MATLAB model or you take a Typhoon model and you generate the codes and dump that into any kind of ECUs or controller.
Suppose there is a PC, several softwares also that is especially designed for power electronic simulations, PCM softwares, and so many simulation platforms are there nowadays.
Mhm.
So users should be able to quick select which one is beneficial for that particular application. I think so.
Correct. So the selection of the platform is essential. Like prior using the platform, you should know what that platform is capable of and why that platform is being used. Then the confusion will be like minimized, what I guess. But for the component level things that I can think of, all if you'll have a bad eye view, then everything boils down to the binaries. Like for me, Typhoon HIL and DSpace, both are like I can work both of them, not because I have worked on them, because I think both of them does the same thing, but specialization of both the softwares are different.
Thank you, Dr. Saurabh. Thank you.
Thank you, sir.
Well, well.
So I think there are no more questions from the participants. In that case, we can conclude the session. And so on behalf of the organizing committee, I extend a heartfelt thanks to our respected resource person, Dr. Saurav Kumar Sahu, for a detailed session, back-to-back 2 sessions, starting from testing of electric vehicles to introduction of real-time simulation environment, like with a case of Typhoon HIL, with a very crisp and detailed demonstration of how we can create schematics and then go to the Hill SCADA environment and view the graphs and responses. Thank you, Dr. Saurav Kumar Sahu. And we also thank you, sir, for graciously accepting our invitation, finding out some time from your busy schedule, sharing your experience with us.
Thank you, sir. I would like to thank the organizing committee for this opportunity as well.
I request all participants to kindly switch on their cameras so that we can take a screenshot with our resource person to capture this moment.
My camera is not working right now.
Okay.
Could you just wait for a moment? I will just rejoin the meeting.
Yes, sir. Yes.
Anyhow, thank you, Dr. Saurabh, sir, for nice presentation.
Thank you, sir. Thank you. Just give me a second.
Yes, sir.
Sure.
Hello, sir.
Hello, welcome back, Saurabh. So I will quickly take some screenshots. Just allow me few moments because I need to take multiple screenshots. Thank you, Saurav sir.
Thank you,
And
sir.
thank you all the participants for patiently allowing me
Thank
to
you,
take
sir.
multiple screenshots. Thank you very much. It was a great session, sir.
Thank you,
Sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you for your
Thank you, Saurabh sir. Very nice
Thank you, sir. Good night,
presentation,
sir.
sir.
Thank you, Prabhat sir.
Thank
If
you
I
very
will
much.
have a
Thank you,
doubt,
sir.
sir, I will contacted with you, sir, in future.
Yeah, sure, sir.
Okay, sir. Thank you.
Okay. Thank you.
Okay, sir. Thank you.
Okay, respected participants, with this we come to the end of
Thank you,
the
sir.
fifth
Thank
day.
you. Okay, sir. Thank you. Good night.
As per schedule, tomorrow the sessions will start from 2 p.m. and the quiz and assessment process will start from 6:30 p.m.
Okay, sir.
Okay, sir. Okay,
And the
Thank you,
assessment
everyone.
will be on the ATAL portal only.
Yes, ma'am. You have to log in through your credentials, and we will share a video of the step to follow so that you can reach to the assessment link also.
Okay,
Okay,
thank
sir.
you, sir.
Okay, sir.
Okay,
Okay,
we
sir.
will share the video through the WhatsApp group, and I will try to share it also through the email ID.
Sir, done.
Okay, sir.
Okay, sir.
Thank you.
Okay.
Thank you.
Okay, thank
Good
you,
night.
sir.
Thank you, sir.
Thank
Good
you,
night,
sir.
sir.
Good night.
Thank you, sir.